So we're going to start off today with another law of thermodynamics, and we're going to weave some review into this. And what we're going to review to start off today is the concept of entropy. Okay, we talked about that last class. Can you guys give me, because there's more than one way to define the word entropy, can you give me some one-word definitions? What's one, Jasmine? What, messiness? What's another? Chaos. Disorder. Randomness. Okay. And we talked about how there is entropy in everything that we come in contact with. Some things have more entropy than others. We talked about how entropy is usually increasing. The universe favors processes where entropy increases. All right, so if we were looking at an ionic compound, for example, this is what it would look like. Okay? Ionic compounds, guys, remember, obviously have charges. Even covalent compounds that are polar have ends that are more negative, more positive. The point here is there's not perfection. There's not perfect organization. Everything has entropy. Do you know the name of this temperature right here?
Absolute zero.
Absolute zero. Okay, well, ladies and gentlemen, absolute zero is a temperature that has not yet been attained. Okay, there are research labs all around the world that their entire goal is nothing more than to eventually achieve absolute zero. Hasn't been done yet. I don't have a number for you, but I feel like there's a lab in Spain. This was maybe a year ago that has gotten the closest that anyone has ever gotten, and it's like within thousandths of a degree. So we're close, but we're not quite there yet. And the thought is, if you were to reach absolute zero, entropy would cease to exist. Okay? Now that's kind of deep thought, deep thinking here. But the thought is, if we were able to reach absolute zero, entropy would become zero. We would achieve perfection, right? It's a thought. You can't prove it yet, but that's the thought. But guys, the point is, since we have not achieved absolute zero yet, which means that we are always at temperatures higher than 0 Kelvin, our entropy values, remember entropy has that variable capital S, entropy values will always be above 0. To prove that to you, okay, I want you to, once again, go to that appendix in the back of your textbook. And guys, we used this chart a couple of class periods ago, but we only looked at one column. We only used this chart for delta H values. Let's just review. What's the fancy word that delta H represents? Heat, which is enthalpy. Yeah, okay. Well, now, since last class, now you know what those other two columns represent. We've got the column that says delta G. Do you remember what G stands for? Gibbs free energy, okay? And then we have the column S for entropy. And I want you to look up two substances, and we'll start with solid beryllium. Please find it and tell me what is its entropy value. Okay. 9.44. What are the units? Joules per mole Kelvin. Okay. And by the way, please don't ask me how you put a number on how disordered something is. I have no idea. Okay, people who are smarter than me have made these decisions. Okay. Here's the second one that I want you to look up. Should be with the carbon compounds. All right. It's a compound called butane. Find it. Tell me the number. The entropy value. 310. Okay. Well, guys, this is a pure element. Okay, just solid beryllium metal. This is an organic compound, butane, all right, which is just a 4-carbon chain with 10 hydrogens attached to it. Okay, this is the gas that's in like a butane lighter, all right? And the point I'm trying to illustrate here is pure element, covalent hydrocarbon here. Doesn't this doesn't that look like a more complex molecule than that? I mean, that's not even a molecule, it's just a pure element. The more complex the molecule or the compound, the higher this number will be. Okay? The more complex the substance you're looking at, the greater its entropy will be. I mean, there's only so messy I can make a pure element. I can make a long hydrocarbon. That has lots of chances for rearrangement and disorder. Okay? So if you just kind of scan your eyes down that entropy column in that chart, you'll notice simple elements have smaller entropy values than compounds, and large compounds have even higher entropy values. That's the point I'm trying to make. Now, does this look familiar to you? It should. It is on the formula sheet. You're absolutely right, which means you don't have to memorize it. That's nice. We saw this formula before. Do you remember what was the only thing that was different when we saw it before? Yeah, it was enthalpies instead of entropies, and I put that formula up and we all went, ugh, that looks awful. And then we realized that it was something actually very, very simple. Just values out of that chart, products minus reactants. The point here is, ladies and gentlemen, you can do the exact same process with entropy values. Okay? So I just wanted you to be aware of that, and yes, it is on your equation sheet, so no need to memorize. So we've reviewed entropy here. Let's review this concept. Okay? Gibbs free energy, sometimes you'll just see it referred to as standard free energy change. Do you all remember from last class, what is the one and only reason that you really ever need to calculate a number for delta G? Why would you need to do that? Yeah.
To find if a reaction is favored thermodynamically.
You got it. To answer the question, if a reaction is thermodynamically favored, yes or no. Okay? What kind of a result for delta G are you looking for it to prove that it is favored? Negative delta G. If delta G comes out to be positive, then the answer is no, it's not favored. Right? And if you come back to your equation sheet in that thermochemistry section, we used an equation last class that's right here. Delta G equals delta H minus T delta S. We used that equation last class. But I want you to be aware that you have other options as to how to calculate delta G. Here is one of them. boy, that sure looks familiar. Okay? You can do that same process with numbers out of all 3 columns in that chart. This is the one we worked with last class. Okay? Later today, we're going to actually learn a 3rd way, and when we get to 3rd quarter, we're even going to learn a 4th way. But let me ask you this. Let's say you come across a test question, and it says, it gives you some information, and it says, is this reaction favored, yes or no? And you say in your mind, okay, I need to calculate delta G. How do you know which equation to use? Yeah, it depends on what's given to you. If you are given values out of the back of the book, because remember, I'm not going to let you get up and just start looking up numbers. If I give you delta G's of formation, then use this guy. If I don't, and I give you delta H and delta S information, then I would use this one. Okay? Remember, guys, if you see that little subscript F or you see the word formation, where should your brain be shouting at you? Chart, 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 chart. Okay? All right. Let's get to a calculation. All right? Close your books. Close them. And when I said to you guys, I'm not going to let you, look up values out of the back of the book, I told you I have to give them to you. How am I going to give them to you? Maybe kind of like this. Right? See, there's the little F. That screams chart. And I'm giving you some enthalpy values. I'm also giving you some entropy values. This question says calculate delta H, delta S, and delta G. Now these two, you're probably not having a hard time figuring out how you're going to get them. This one, you'll have to look at what information do you have. This is why I had you close the book. You'll have to look at what information do you have at this point and how are you going to get it. Go. One word of caution here. Be careful with your units. Be careful. I'm not trying to be cruel. This is how these units are given in that chart. Now, will the units matter right at the beginning of the problem? No, but they're going to matter more towards the end. You'll see when you get there. Okay. Check and see how you did. So, guys, when I said to you, be very careful with your units, at this stage right here, it actually didn't matter, okay? Using the values given to me in the chart, my delta H would come out in kilojoules. Using the values given to me in the chart, delta S would come out with joules per Kelvin. And that's fine. The problem comes when you need to take these two values and plug them into the same equation. You can't put two different units of energy into the same equation. So what I chose to do was change this guy from kilojoules into joules. You didn't have to do that. You could have left that in kilojoules and changed this one to kilojoules. So you have some options there. Thank you. Does my final answer have to be in kilojoules? No. As long as you round your final answer to 3 sig figs, you're good to go. Okay. You could have rounded this like with scientific notation, 1.42 times 10 to the 5th power. Yeah, 5th. Oh, you know what? And the temperature. Actually, it should have 2 sig figs. Because the number 25, as in 25 degrees Celsius. So actually, my fault. This should have 2 significant figures, not 3. Okay? All right, so very much like on the test, okay? These two, I had given you values out of the chart to find delta G. You didn't have the option of looking in the chart. That's why I asked you to close the book. The only option you had was to plug in these guys and use that equation. All right, now, do you guys remember from chapter 5, we did that challenge problem? It was a Hess's law problem, okay, which a lot of you like. I like them too. All right, the thing is, when we did Hess's law problems, we were rearranging equations with enthalpy values. You can do the exact same process with free energy values. Same process. Let's just review. Let's review a little vocabulary. In a Hess's law problem, I've given you 2 equations here. Do you remember what these equations are called? Elementary steps. Very good. So I've given you 2 elementary steps. Here's my overall reaction. Let's just do a quick Hess's law review. This is an easy one. The thought process is start with your overall equation. Okay, carbon diamond. Here it is. Is it on the correct side? Does it have the correct coefficient? Okay, so I'm going to leave this first equation alone. Carbon graphite, as in what's in your pencils. Here it is. Is it on the correct side? So what do we do? Flip it around. Okay. And when we flip an elementary step around, what happened to the delta H values when we did that? Change of sign, guess what? It's the exact same process. This just becomes positive 394. I'm going to scribble through this middle one because I don't want to get confused. I don't want to think that I need to use that. Okay. What can I cancel out? Okay, CO2 is gone. O2 is gone. Am I left with the equation that I want? And you don't even need a calculator. What's my delta G value? -3 kilojoules. Okay. What does a negative delta G mean again? It's favored. It's thermodynamically favored. Can you give me a word that the College Board does not like that would be kind of a synonym for that? It's spontaneous. Now guys, I chose this example for a very specific reason. Look at this reaction. Diamonds are turning into what's in your pencil on their own. It's kind of weird. So if you have any jewelry with diamonds in it, do you need to worry that like one morning you're going to wake up and your precious diamond earrings have morphed overnight into graphite earrings? I mean, it's spontaneous. It will happen, people. Now, is it going to happen tomorrow? No. It might happen a million years from now. You'll be dead. I'll be dead. I'll be dead too. Who cares? Okay? The reason I did this is to point out the fact that just because a reaction is favored, spontaneous, will happen on its own, doesn't mean it's going to happen quickly. Okay? Spontaneous reactions, this isn't giving us any information about how quickly it occurs. We're going to get to a chapter probably February-ish that's on the topic of kinetics, and that is all about how fast reactions occur. Some are very fast. This would be an example of one that's very, very slow. Okay. Now, you have a choice here. You can write that equation down if you want, but you don't have to. This is an equation that used to be on the equation sheet. It is no longer. Calculations with this used to be on the AP exam. They are no longer. However, the concept behind it is on the AP exam. So we're not going to do calculations with this, but I want you to understand the situation behind it. Okay? And I'm going to ask you a lot of the same questions over and over again today. You're going to get sick of me asking these, but it's good for you. What's the purpose of solving for delta G again? To see if something is favored or not. Okay, well this equation has delta G twice. What's the difference? Yeah. This one, that symbol, that means under standard state conditions. So this one must be at non-standard state conditions. All right, well let's review that. If you go back and look at your notes from the beginning of this chapter, what are standard state conditions? What is standard state pressure? 1 atmosphere, okay. What is standard state molarity? 1 molar, okay. Easy numbers to remember. What is standard state temperature? 25 degrees Celsius. What's so special about that? That's room temperature, in theory. Okay, so what if you have a reaction where all of the gases are at 1 atm, all of the aqueous things are at 1 molar, but the temperature isn't 25 degrees, maybe it's 29 degrees. Crisis. Do you just throw up your hands and say, oh, I can't figure out if it's favored or not. I quit. I'm throwing my pencil down and I'm walking out. No. Right. No, ladies and gentlemen, you wouldn't do that because you're better than that. There is a delta G you could solve for. Okay? It just would be delta G under non-standard conditions. Because guys, in whatever your situation, if you take even one thing out of standard state conditions, like you just change the temperature, then the whole system is not at standard state anymore. As I said, are we going to calculate anything? No, but we're going to see some questions that are conceptual. Now, capital Q, for those of you that have the slides, it's written there. We've seen it before. It's something called the reaction quotient. Let's see what you remember. We saw the reaction quotient back in the equilibrium chapter. Remember, we said this is calculated exactly the same way as K. The equilibrium constant is calculated. Do you guys remember what makes Q and K different? Good. Q is conditions not at equilibrium, whereas K is at equilibrium. Okay? So, calculations not on the exam, so what will be on the exam? Something that looks like this. All right? We've got a reaction. It's already balanced for us. It says, indicate whether delta G, please notice, ladies and gentlemen, there is no degree symbol there. Okay? Indicate whether delta G increases, decreases, or does not change when the following changes are made to the reaction above. And then it's like a little hint. Think Le Chatelier's principle. Okay, and I've got a little typo here. This should be a double-headed arrow. What does a double-headed arrow mean? We're at equilibrium. Okay, we're at equilibrium for the time being. I'm about to make it so that we're not anymore. Okay, and I'm going to walk you through the thought process because this can be a little bit confusing. Let's look at number 1. It says carbon monoxide gas is added. Well, that's changing really 2 situations. Number 1, if I dump in more of this reactant, number 1, I'm no longer at equilibrium anymore because I've messed that up. I'm also not under standard state conditions either. Okay, because let's say both of my reactant gases were at 1 atmosphere and everything was at standard state and everybody was happy. I've now added more gas. This isn't going to have a pressure of 1 atm anymore. Okay, but that's okay. Tell me, this is just review, which way will this reaction now shift to get back to equilibrium? To the right. You are correct. Okay? All right, I think this is now the 3rd time I've asked you this, and I will ask it again, so yeah. What does a negative delta G mean? The reaction is favored. Okay, let's be more specific. When you say delta G negative, reaction is favored, let's be more specific. That means the reaction in the forward direction is favored. Okay? When we say a reaction is favored, we don't mean that it could go this way or it's also favored this way. When we say a reaction is favored, it means it's favored in the direction it's written, from left to right. Now look what we have just done. We've messed something up which has caused this to shift even more in that forward direction. What do you think will be happening to delta G? Have we done, whatever we've done here, have we made this reaction more favorable, less favorable, or just stay the same? We've made it more favorable. So what should be happening to this number? Will it be becoming more negative, more positive, or staying the same? More negative. That is confusing sometimes. We caused a shift in the forward direction. We're causing this reaction to be more favorable than it was before. More favorable means more negative. Okay? Let's do another one. This time, I'm going to take something out. I'm going to remove some hydrogen gas. First of all, which way will this shift? To the left, you got it. That's causing a shift in the direction that I don't want to go in. Right? Think of the forward direction as the direction you want to go in. I'm doing something to oppose that. What I have done here, guys, am I making this reaction in the forward direction? Am I making it more favorable, less favorable? No change. Less favorable. So what should be happening to delta G? It should be going up. Because the more positive that number, the less favored the reaction is. This is good review from our equilibrium chapter. Let's see what you remember. Pressure is increased. Now don't tell me left or right yet. Which way does it go? Just generally. If you increase the pressure, which side do you shift toward? Less moles, thank you. Less moles of gas. Thank you for saying of gas. How many moles of gas are on the left? 3. How many on the right? 0. So I must be shifting to the right. That's the direction that I want to go in. So what's happening to delta G? It's decreasing. Okay. You guys are doing great. Let's keep going. This time, the change that I'm going to make, I'm changing the temperature. And remember, guys, when we first started looking at Le Chatelier, I said to you, you cannot answer a temperature question unless I give you some additional information. Well, here it is. Tell me now, what am I saying in this set of parentheses? This is an exothermic reaction. Anytime you're given information like that, just get in the habit, come up to your equation, write the word heat in wherever it should go. And where should it go? On the left or the right? The right. Exothermic means heat is released, produced. Temperature is increased. It's going to get hot. Are we adding heat or taking heat away? Adding. Okay, and where is heat? It's a product. Which way will this shift, ladies and gentlemen? You got it. So what's happening to delta G? It's becoming more positive, increasing. Okay, last one, just to make sure that you've got it. This time I'm going to change the product. I'm going to add more product. Which way will this shift? Aha! You fell for it, some of you. Liquids, no effect. What other state of matter would have no effect? Solids. No effect or no change. So that's what you would have to do. No calculation, but you will have to predict what's going to happen to delta G. Okay. Now, we talked about this last class, briefly, like right at the very end, about how if you are at equilibrium, delta G, please notice, non-standard, is equal to 0. Okay? We talked about that in the very last problem that we did. Again, if you don't want to write this down, that's fine, but there is an equation that you are responsible for knowing that is on your equation sheet that comes from this. And for you mathy types, I want you to understand where this equation comes from. Let's say we are at equilibrium. That means this guy is equal to 0. And if we're at equilibrium, it's not Q. What would it be? You got it. If I rearrange this equation, it looks like this. And that is on your equation sheet, and you will have to use it. Okay? I'll explain a few things here, but let me just first call your attention to the fact that we now have 3 ways to calculate delta G. We could do products minus reactants. I could do the one we did last class, delta H minus T delta S, and now I have a third way. Depends on what you're given. Do you guys know what this is? We've seen this before. It's the gas constant. Do you have to memorize the possible values? No. They're there. Do you think it matters which one you use?
Yes.
It does. Tell me this. What kind of units do we see for delta G a lot? Like what unit of energy? Joules. Look at your possible values for R. There's only one of them that has joules in it. Which one? 8.314. You have to use that. Which means you can't put kilojoules there gotta be in joules if you want to use that number. T is temperature. What unit does it have to be in? Kelvin. I know that because there's units of Kelvin linked up with 8.314. This is a natural log. Okay? And guys, if you are a person that is kind of uncomfortable with like log base 10 and natural log, in all honesty, it's not my favorite thing to work with. Do not fret. All right? We're not going to be doing crazy log functions and graphing and inverse. No. Okay? The AP exam requires you, basically, can you push the button on your calculator? Yes, you can. All right, I just put this in yesterday, so for those of you that have the PowerPoints, you won't have this, but we are doing a problem together from your problem set right at this moment. Which means there's no excuse for anyone getting below a 1 on the next problem set. Okay? Let's talk this one out, and then I'm going to let you solve it from there. Okay, this is number 83 from your problem set, and I'm changing it just a little bit, okay? But this is the equation given to us. Is it balanced? Yes. Okay. Using data from that chart in the back of the book, if this were a test question, I would say using data given to the right or something like that. Calculate the equilibrium concentration of CO2 at 298 Kelvin. There is a part B to this question, but I want you to omit it. We're only going to do just this part. Okay, now here are some context clues here, ladies and gentlemen. We're in this thermodynamics chapter right now. What is the only equation we have worked with that has anything to do with equilibrium? Hint, hint, we just talked about it 30 seconds ago. This one. Okay. So when you're dealing with a thermochem or thermodynamic situation and you see equilibrium mentioned, chances are you're probably going to be using this equation. Let's look at this and think, what do we have and what don't we have? Given what we are in the problem, or given what we have access to, do I have a way to find this? Yes or no? Yeah, how? What are we going to do? Using the chart, products minus reactants. Okay, sounds good. Let's put a check mark. I have a way to get that. Do I have R? Yep. Do I have a temperature? Okay. So guess what? That's my unknown. Let's start there. That's not the end of the problem, but let's start there. If any of you are uncomfortable, I'm probably using the wrong word here. If you're uncomfortable, like undoing a natural log, I'll help you with that. But I imagine many of you are comfortable and can solve for an unknown tied up with a natural log. But let's get to this point. Let's solve for K, and then we'll stop there for a moment. Before we even look at the end of this problem, because this is not the end yet, something that you have got to be really careful about in this chapter, and I've said it a number of times, units. When you do products minus reactants, with the values out of the book, back of your textbook, your answer is going to come out in kilojoules. You can't plug kilojoules in right there and use that number, because this has joules tied up in it. So I had to convert this into joules. Now, at this point, and if you got something slightly different like negative 88, something, that's fine. We're close enough. Do we need to go into the nitty-gritty details of how to undo a log? No, we're not, okay? All you have to do in your calculator, second ln, natural log. Do you see in the screen that it says lowercase e to the power of blink, 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 and it's waiting for you to put a number in there? That's the number you put in there. Hit enter. When you do that, you're going to get something in this neighborhood. It might not be exactly the same. K doesn't need units. And yes, that is an exceptionally small number. Okay? Very, very small. Now, that's not the end of the problem, but we're very close. Okay? Let me come back. I'll come back to this screen, but guys, can you tell me, please? What would be the equilibrium expression for that reaction? Why the concentration of just CO2? I mean, where's the rest of that equation? They're solids. They're excluded. So guess what? Calculate the equilibrium concentration of CO2. I just did. It's equal to K. So let me come back and finish this problem. Now, and this gets into the very last thing that I want to talk about in this chapter. This is an exceptionally small number. Would you agree? Okay? I want you to think about what that means. Equilibrium constants, aren't they always products divided by reactants? Nod your heads. Okay? Think about what that means if that is a very, very small number. Actually, let me write it a different way. Does that mean large amount of products or small amount of products? Very small. So that products over reactants might look something like products over like that. Okay? And let's go even further with that. If this is my situation, is this a reaction that is moving a lot in this direction? No. I'm making barely any products. It's dominantly moving this way. What do you think that means about how favorable this reaction is in that direction? It's not very favorable. And guys, look at what delta G equals. It's positive. And that's a big positive number, by the way. Very positive delta G means not favored at all. Yeah, you bet it's not favored at all. I mean, look at that. All right? We're making connections here, people. We're bridging equilibrium, favorability. This is big time. Thank you for saying that. He said, if delta G is a positive number, will the K value always be less than 1? Yes, it will. Always. Now, K cannot be negative. But if this is positive, this guy will be between 0 and 1. It'll be a fraction. Very good. If this is negative, then K will be greater than 1. Which, he just literally said exactly what this chart says. A very positive delta G means a very, very small K value. Maybe you want to write in there, like on that line, not favored. all. Whereas down at the bottom, a very negative delta G, very large K value, very favorable. Okay? So you could see questions like this in free response where you're actually calculating something, or you could see it in multiple choice where you could just understand it conceptually. Like maybe they give you a very, very negative delta G value, and then the multiple choice answers say, which of the following is a possible value for K? You're looking for the largest one. Okay. Ladies and gentlemen, that is the end of the chapter.